Okay, so this video is meant to introduce you to the concept of waves, different way of looking at things. So let's first off start by distinguishing a particle versus a wave, because they are kind of different concepts, and so far we've just been dealing with particles. So a particle is essentially a tiny concentration of matter. Okay. And it is capable of having energy, right? Whereas a wave is a distribution of energy that can travel through particles. Now, some waves need particles. Some waves don't need particles, but trying to distinguish the difference between a particle and a wave. So a wave is a distribution of energy that can go from one spot to another spot, okay? A particle is a concentration of matter that can have energy and can transmit energy. Like from one object to another object, okay? So as we kind of zoom in now on our focus of waves, it's helpful to understand that there's two classifications of waves, types of waves. There are what are called mechanical waves and electromagnetic waves. And mechanical waves are waves that are governed by Newton's laws. Essentially, they have to obey all of our laws from mechanics. And mechanical waves require a medium or like a vessel to travel through. Okay? So they require a medium or particles. So examples of mechanical waves, like water waves. They're ocean waves. They require the water to transmit the energy. I can't spell today. Sound waves. Sound waves. We can't see sound waves, but sound waves require a medium. If there was no medium, then the wave couldn't be transmitted. So essentially, like with a sound wave, we'll get into sound waves in another lesson. But for a sound wave to get transmitted, something has to make the wave. So in the case of me speaking, my vocal cords are making the wave. And then that wave is causing particles to oscillate and oscillate and oscillate. And so all throughout these air molecules, those air molecules are moving and moving and moving until they reach your eardrum, okay? If there were no air molecules, then that sound could not get transmitted from one spot to another spot. So mechanical waves are examples of waves that they have to have a medium in order to get from here to there. In order to transmit the energy from here to here, there has to be some kind of a medium in between. Electromagnetic waves. These are waves that comprise the electromagnetic spectrum. And key difference is these waves do not require a medium to travel through. They can go through a medium. Like light waves can go through air, but they don't need air to get from here to there. So electromagnetic spectrum is given off by the sun. All the different waves are given off by the sun. And those waves can get from the sun to the earth with pretty much a vacuum in between. Okay? So review of a little bit of chemistry, physical science background knowledge. If you think about the E&M spectrum, so if you think about the electromagnetic spectrum, we have our big waves, which are radio. Then we have our microwaves. We have infrared waves. we have good old visible light. Within visible light is Roy G. Biv. This is the color spectrum that we are used to seeing everything in. After visible light, we have UV rays. Then we have X-rays. And then we have gamma rays. Okay. Going in this direction, we have what's called low energy or low frequency. And going in this direction, we have high energy or high frequency. Okay. We're most familiar with visible light because that's what our photoreceptors in our eyeballs can detect. We can detect visible light rays. Our skin cells, our sense of touch, can detect infrared waves. We detect that as like a temperature differential. So we have the capacity to kind of sense that with the infrared. But we have no other sensors within our body that can detect any of these other waves. Our body can definitely be affected by the waves. So our bodies really aren't affected by like these in terms of like harmful. Microwaves, there's a little caveat, I'm going to put a little asterisk on microwaves in terms of how they can harm us, but just in terms of their pure energy, they don't have enough energy to really harm our cells. As we go into the waves that are above visible light, UV rays, X-rays, gamma rays, these definitely have the potential to harm us if we have too much exposure to the energy. So, for example, for a UV ray, we can go stand outside, and if we have a small amount of exposure to the UV ray, we're not going to get too much harmful damage from that energy. But the more we get exposed to the UV rays, they tend to cause damage within our cells. And as our cells then begin dying, we feel the effects. So like you get a sunburn, you don't really feel hot and that warm sensation from a sunburn until a couple hours afterwards. And that's because the damage is being done, and then the cell begins to die, and we see the after effects. X-rays, it doesn't take as long of an exposure to cause that damage to our cells, and gamma rays, it's a pretty quick exposure and we have damage to our cells. If you have radiation treatment to destroy cancer cells, it's usually X-rays or gamma rays that are targeted to a specific spot in your body to kill those cancer cells. So these waves, these electromagnetic waves, do not require a medium to travel through. We are going to focus our kind of understanding for this first unit of lesson with mechanical waves because we can see them. We can visualize them. They're a lot easier for us to understand. We will go into a lot more depth with light waves when we study optics. Okay, but for now we're just going to study mechanical waves. So when we think about mechanical waves, there are two different types of wave forms that a mechanical wave can take. The first is called a transverse wave, and this is when the direction of the wave movement is perpendicular, and I'm just going to do the symbol because that's a long word. When the direction of the wave movement is perpendicular to the movement of the medium. Okay, so remember, mechanical waves require a medium to travel through, and as that wave is traveling through the medium, the particles within that medium, they have to move. As they're transferring the energy, they're going to move. So a transverse wave is when it's perpendicular. So visual-wise, it's like if I've got a string and then I send a wave pulse, and my wave is moving in this direction, like the energy from my wave is in this picture moving horizontally, but my medium moves up and down, okay? So let me demonstrate that, try to demonstrate that with my slinky of science. So if I'm gonna send a wave pulse from like my top hand down here to my bottom hand, a transverse wave would be if I made my medium move. It doesn't work as well when there's only one person, when it's not a very long distance. My medium moves perpendicular. So like this is a perpendicular movement in that my medium is moving this way, but my wave is going this direction. I could also, I don't know if you'll see it dimension in the video, but I could make it move like that. And in this case, my medium moves that way, my wave is moving that way. So that's a transverse wave. Ocean waves. Ocean waves are transverse waves because the water physically goes up and then down as the wave is traveling forward, okay? Longitudinal is when, and they're also known as compression waves, longitudinal waves are when the direction of the wave movement is parallel to the movement of the medium. So in this case, it's as if like if my wave is going in this direction, my medium also has to move in that direction. And so that's a little easier for me to model here by myself. I may like pause the video and switch in another video to show you a little bit better view of this. But again, I'm going to send my wave pulse from the top down to the bottom, and if I were to do it longitudinally, it's like doing it like this. Okay, so I'm like scrunching this little bit of these coils, and that scrunch gets like moved down further and further and further. Okay, so this is kind of like the comparison. So this is a longitudinal or compression wave versus a transverse wave would be like a movement, like a side-to-side movement, okay?
Okay, so this simulation does a pretty good job explaining the concept of a transverse wave. So in this idea, the wave is moving to the right, like the energy is moving rightwards, but the particle is physically moving up and down. So this is where my particle movement versus my wave movement is perpendicular. And then they've got one for the longitudinal wave. And so you can kind of see how in this case, my wave is moving to the right, but an individual particle is moving right and then back left, right and then back left. So its movement is parallel.
Okay, so let's review a little bit of wave terminology. We studied these ideas when we first studied oscillations, but now we're going to apply them to our waves. So recall that amplitude is the maximum movement from equilibrium. We just symbolize it with a capital A to stand for amplitude. And in the case of our waves, we're going to see that this amplitude, for sound waves at least, is akin to like a loudness. For a light wave, it may be akin to like a brightness. And then recall that the period, or the frequency, so let's go for the period. Period is the time for one cycle. Or we can kind of think of it as the time for one wave to go by. And the frequency would then be the number of waves that goes by in 1 second. So, where'd my eraser go? I have no eraser. Let me get rid of my spectrum here. So recall that period, remember the symbol for period is capital T. The units are just seconds. For frequency, the symbol is a lowercase f. There was an equation that related the two, that frequency was equal to 1 over the period. And then my units would just be 1 over seconds, and that was equal to a hertz. Okay. So again, things we have studied already, but just kind of reminding you of these things. Now, in terms of focusing on how these apply to waves, for a wave, the wavelength of a wave, pretty difficult definition, is the length of one wave. it's got a weird symbol. It's the Greek letter lambda. It's kind of like an upside down Y. Okay, so this is lambda. Let me draw it large and in charge here. Okay, so that's lambda. And if I were to kind of think about my wave movement, okay, so if this was a time graph, the period would be the time for one wave. Okay, if this was a distance graph, like a position graph, this would be one wavelength. Okay, and then amplitude would be like the height of this wave from equilibrium. Okay, so the symbol is just a lambda, stands for length. Units are just the units for distance, so you could have it in terms of meters, in terms of centimeters, etc. Now, if we think about the quantities we've looked at, and I think about the idea of a wave speed, how fast is a wave travel? Okay, so this is well, there's not really a need to define it. Wave speed is the speed of the wave, and that seems redundant, so I'm not going to write that down. If I think about my traditional equation for velocity, velocity is distance over time. Well, in this case, my distance of one wave is a wavelength, and the time for one wave is the period. But recall that frequency is just 1 over period. So that means I could represent my wavelength as lambda times frequency. And this is often the form we see for wave speed, the wave equation, where the speed of my wave is equal to the wavelength of my wave times the frequency. Okay? So that is a basic introduction to the concept of waves, and then we'll kind of dive into our focus with mechanical waves and then light waves.